From the backyard of our own solar system to the distant shores of the cosmic ocean, the universe is full of mysteries. It has always been like that. Thus, although astronomers understand certain aspects of the universe clearly, others are more muddled. The Big Bang has a mountain of evidence behind it, while the picture of how proto-galaxies evolved into normal galaxies in the first few billion years of the cosmos is just coming together. But what exactly happened at the end of the cosmic dark ages following the Big Bang that brought together the seeds of matter to form the first stars and galaxies? That question is still wrapped in a hazy cloud of mostly speculation. At the core of the issue is, which came first, the galaxy or its monster black hole? Technically, it's an even more ancient riddle than the one about the chicken or the egg, though we've only relatively recently become aware of it. But now, thanks to the latest discovery from James Webb, scientists may finally have an answer. A brand new analysis of Webb data revealed that black holes not only existed at the dawn of time, they birthed new stars and supercharged galaxy formation. The insights upend theories of how black holes shape the cosmos, challenging classical understanding that they formed after the first stars and galaxies emerged, and offer a new perspective on cosmic evolution. Join us as we dig deep into how James Webb could completely shake up what we know about the early universe. Black holes are enigmatic astronomical objects, areas where the gravity is so immense that it has warped space-time so that not even light can escape. It was not until the detection of quasars, which allow astronomers to see the light emitted by matter falling into black holes, that we had evidence that they were real objects and not just mathematical curiosities predicted by Einstein's general theory of relativity. Today, we know the universe is filled with them. Indeed, by combining information about stars, black holes, and stellar and cosmic evolution all together, astronomers have the first robust estimate for black holes in the universe: 40 quintillion. It's more than almost anyone expected. Notably, a few of those black holes are truly enormous, with masses millions of times greater than the Sun. Current theories suggest that black holes form via two distinct channels. According to the first pathway, they are stellar corpses, so they form when massive stars die. Stars whose birth masses are above roughly 8 to 10 times mass of our Sun, when they exhaust all their fuel, their hydrogen, they explode and die, leaving behind a very compact, dense object, a black hole. The resulting black hole that is left behind is referred to as a stellar mass black hole, and its mass is of the order of a few times the mass of the Sun. But not all stars leave behind black holes. Stars with lower birth masses leave behind a neutron star or a white dwarf. Another way that black holes form is from the direct collapse of gas, a process that is expected to result in more massive black holes with a mass ranging from 1,000 times the mass of the Sun up to even 100,000 times the mass of the Sun. This channel circumvents the formation of the traditional star and is believed to operate in the early universe and produce more massive black hole seeds. And for decades, astronomers argued that the very first stellar black holes formed when the earliest supermassive stars came to the end of their lives. Those stars have often been characterized as monsters and loners in the infant universe. They lived very short lives and exploded in hugely catastrophic supernova events, blasting most of their outer layers out to space. The remaining cores collapsed and created some of the earliest stellar black holes. Black holes likely combined and accumulated more matter, forming the seeds of the first supermassive ones at the hearts of galaxies. At the same time, the conventional wisdom about galaxies said that they formed when giant gas clouds collapsed. Waves of star formation followed, and presumably, more stellar black holes. That conventional wisdom isn't completely wrong. However, it doesn't explain the supermassive black holes that existed so early in cosmic time, long before they should have. That's something astronomers are still working to understand. But this is where James Webb plays its role. A reanalysis of data from the Webb telescope indicates that these black holes could have been present during the first 50 million years of our 13.8 billion-year-old universe, driving star formation at such an early age. The findings could challenge the idea that black holes formed only after the first stars and galaxies emerged. As Joseph Silk, team leader and a professor at Johns Hopkins University, said in a statement, "We know these monster black holes exist at the center of galaxies near our Milky Way, but the big surprise now is that they were present at the beginning of the universe as well, and were almost like building blocks or seeds for early galaxies. They really boosted everything, like gigantic amplifiers of star formation, which is a whole turnaround of what we thought possible before. So much so that this could completely shake up our understanding of how galaxies form." Silk points to the fact that distant and early galaxies the James Webb Space Telescope has been looking at, since it started sending data to Earth in the summer of 2022, are brighter than expected. This suggests the galaxies are already replete with unusually high numbers of stars and supermassive black holes. If true, that'd mean our current theories of how galaxies grow may need revision. Silk and his team argued that black hole outflows crushed gas clouds, turning them into stars and greatly accelerating the rate of star formation. Otherwise, it's very hard to understand where these bright galaxies came from because they're typically smaller in the early universe. Why on earth should they be making stars so rapidly? Currently, the most widely accepted theories of cosmic evolution suggest early universe black holes were born when highly massive stars ran out of their fuel supplies needed for nuclear fusion. In turn, those stars would have collapsed and created black holes in later epochs of the universe. This means the black holes would have had to come after the formation of the stars that birthed them, as well as before the first gatherings of galaxies. However, Silk and colleagues found that black holes and galaxies seem to have coexisted during the ancient universe, influencing each other as early as 100 million years after the Big Bang. This time period would be equivalent to merely the first days of January if the history of the universe were condensed to a calendar year. The immense gravitational influence of black holes means that nothing, not even light, can escape its outer boundary, known as the event horizon. What this means for us is that whatever lies beyond that boundary can't be seen directly. But beyond the event horizon, things still happen. A black hole's gravity is still intense enough to generate violent conditions for any surrounding matter with the misfortune of falling too close to the event horizon, heating it and causing it to flow brightly. This matter can be swallowed, or it can be channeled to the poles of the black hole, where it is blasted out at near light speeds as jets or winds. Black holes actively feeding on matter like that can power what are known as active galactic nuclei, or AGN, a region within galaxies that can outshine the combined light of every star in the galaxies themselves. Silk thinks the fact that black holes act like cosmic particle accelerators in this way is what enabled the Webb telescope to spot so many in the early universe. We can't quite see these violent winds or jets far, far away, but we know they must be present because we see many black holes early on in the universe. These enormous winds coming from the black holes crush nearby gas clouds and turn them into stars. That's the missing link that explains why these first galaxies are so much brighter than we expected. The team behind this research theorized that the early universe had two distinct phases. The first phase would have seen high-speed outflows from black holes accelerating the birth of stars. The second phase would have begun when these outflows petered out. Following this, when the universe was around a few 100 million years old, massive gas clouds would have been forced to collapse via intense magnetic storms caused by supermassive black holes. This would have triggered a new period of intense and rapid star formation that far outstripped rates of star birth seen in more modern galaxies. Star formation would then have been stymied because massive outflows from supermassive black holes would have transitioned into a state that conserved energy, cutting off the gas supply in galaxies where stars could form. As Silk explained, we thought that in the beginning galaxies formed when a giant gas cloud collapsed. The big surprise is that there was a seed in the middle of that cloud, a big black hole, and that helped rapidly turn the inner part of that cloud into stars at a rate much greater than we ever expected. And so the first galaxies are incredibly bright. Not only does the team think future James Webb data could provide more accurate early star and supermassive black hole counts that will confirm the new theory, but the researchers also believe the $10 billion space telescope can deliver some answers to fundamental questions found closer to home. As Silk concluded, the big question is, what were our beginnings? The Sun is one star in 100 billion in the Milky Way galaxy, and there's a massive black hole sitting in the middle too. What's the connection between the two? Within a year, we'll have so much better data, and a lot of our questions will begin to get answers. And, as expected, while James Webb has already proven itself adept at peering into the past by imaging objects at tremendous distances, a new breakthrough may have seen the powerful instrument act almost like a scientific crystal ball, staring into the far future of the solar system. The telescope has performed its prognostication when it made a possible rare direct direction of two extrasolar planets, or exoplanets, orbiting two different dead stars, or white dwarfs. Not only do the planets strongly resemble solar system gas giants Jupiter and Saturn, but the white dwarfs also serve as analogues to the Sun's destiny. When the Sun transforms into a white dwarf itself, the change will likely destroy the inner solar system planets, all the way out to Jupiter. According to Susan Mullally, lead author of the research and an astronomer at the Space Telescope Science Institute, very few planets have been discovered around white dwarf stars. What is extraordinary about these two candidate planets is that they are more similar to planets in our outer solar system in temperature, age, mass, and orbital separation than any planets previously found. This offers our first chance to see what a planetary system looks like after its star dies. The planet candidates were directly observed by the James Webb's MIRI as they orbit the white dwarfs WD12022232 and WD210582. One exoplanet candidate is located at a distance from its white dwarf host that's equal to about 11.5 times the distance between the Earth and the Sun. The other candidate sits further from its dead stellar parent, at a distance of about 34.5 times the separation between our planet and star. The masses of the planets are currently uncertain, with Mullally and colleagues estimating them to be between 1 and 7 times that of Jupiter, the most massive planet in the solar system. When the Sun exhausts its fuel supply for the nuclear fusion processes occurring at its core in around 5 billion years, it will swell up as a red giant. Nuclear fusion, however, will continue in its outer layers. This will see those outer layers of our star reach out as far as Mars, swallowing Mercury, Venus, Earth, and possibly the red planet itself. Eventually, these outer layers will cool, leaving a smoldering stellar core, now a white dwarf, surrounded by a planetary nebula of exhausted stellar matter. However, these exoplanet detections, hint at what could happen to the planets beyond Mars, the gas giants Jupiter and Saturn, when the Sun dies. Our Sun is expected to turn into a white dwarf star in 5 billion years, and researchers expect that planets to drift outward into wider orbits after a star dies. So, if you wind back the clock on these candidate planets, you would expect these to have had orbital separations similar to Jupiter and Saturn. If we are able to confirm these planets, they will provide direct evidence that planets like Jupiter and Saturn can survive the death of their host star. Further, the white dwarfs at the heart of this discovery are polluted with elements heavier than hydrogen and helium, which astronomers call metals. This could hint at what will happen to the bodies in the asteroid belt between Mars and Jupiter after the Sun dies. As Mullally explained, we suspect that the giant planets cause the metal pollution by driving comets and asteroids onto the surface of the stars. The existence of these planets strengthens the connection between the metal pollution and planets. Since 25% to 50% of white dwarfs show this kind of pollution, it means that giant planets are common around white dwarf stars. As such, any asteroids that do survive the death of the Sun could find themselves pelted at its corpse by Jupiter and Saturn. The dual discovery is impressive beyond what it predicts for the future of our planetary system. It also simply represents a rare scientific achievement. Since the discovery of the first exoplanets in the mid-1990s, astronomers have discovered around 5,000 worlds orbiting stars outside the solar system. According to the Planetary Society, as of April 2020, only 50 of these exoplanets had been discovered with direct imaging. That is because any light from a planet at such vast distances is usually overwhelmed by the intense light from that planet's parent star, making directly spotting an exoplanet similar to sighting a firefly sitting on the lit lamp of a lighthouse. As a result, exoplanets are usually seen by the effect they have on the light of their star, either by causing a dip in light output as they cross, or transit, the star's face, or through a wobble motion created as the planet gravitationally tugs on the star. These indirect methods tend to favor planets much closer to the star. Direct imaging is better at finding planets farther away from the star, at wider orbital separations. By spotting these planets directly, the Webb telescope has opened up the possibility of studying these worlds further. Scientists can now start investigating things like the composition of the planet's atmospheres and directly measure their masses and temperatures. Mullally added that not everything she and her team discovered about these exoplanets was expected, and that these quirks could change how astronomers think about exoplanets like these in general. Alternatively, the strange features of the targeted worlds could offer tantalizing hints in the direction of long-sought exomoons. As Mullally concluded, if these are planets, then it is surprising that they are not as red in the mid-infrared as we might expect. The amount of light collected by James Webb at 5 and 7 microns is brighter than we might expect, for both exoplanet candidates given their age and how bright they are at 15 microns. This might challenge our understanding of the physics and chemistry of exoplanet atmospheres. Or maybe it means there is another source of light, like a heated moon orbiting the planet. The team's research is available as a preprint on the research repository site, RCKV. While our views of the universe using James Webb are changing astronomy, the forthcoming Vera C. Rubin Observatory will never leave Earth itself, but the highly detailed, big-picture view of the cosmos it will offer. Scientists may very well kickstart a new era of space exploration. The solar system is filled with billions of small, rocky bodies and icy objects, many of which formed around 4.5 billion years ago when planets like the Earth were forming around the Sun. Space missions like NASA's OSIRIS-REx, Lucy, and Psyche have been making strides in visiting these primordial solar system bodies. They've been collecting images, and OSIRIS-REx even snagged a few samples for investigation here on Earth, all informed by data collected by observatories across the globe. Rubin, which will see its first light in 2025, will be capable of detecting millions of new asteroids, comets, and potentially even bodies passing through our planetary backyard from other systems. Take Oumuamua, for instance, which was first spotted in 2017. After detecting these bodies, Rubin will then quickly track them as they move around the solar system and tread close to Earth, or even if they remain in the main asteroid belt between Mars and Jupiter. As Siegfried Egel, assistant professor at the University of Illinois Urbana-Champaign and lead of the Inner Solar System Working Group within the Rubin Solar System Science Collaboration, said in a statement, "Nothing will come close to the depth of Rubin's survey and the level of characterization we will get for solar system objects. It is fascinating that we have the capability to visit interesting objects and look at them close up. But to do that, we need to know they exist and where they are. This is what Rubin will tell us." The observation will monitor solar system bodies and cosmic objects that quite far out, beyond even the limits of the solar system and the Milky Way galaxy, as it conducts its 10-year legacy survey of space and time. Scanning the entire southern hemisphere sky every few nights with an 8.4-meter, fast-moving telescope and the largest digital camera in the world, Rubin is expected to vastly increase our catalog of known solar system objects that has been built over 200 years, by at least 5 times. Not only will Rubin, presently under construction on the mountain Cerro Pachon in northern Chile, spot a multitude of new solar system objects, but scientists also expect it to gather more information about the broader spacescape of the solar system. This could reveal whole regions that contain unique objects to consider as future space mission targets. As Egel said, if you think of Rubin as looking at a beach, you see millions and millions of individual sand grains that together constitute the entire beach. There might be an area of yellow sand or volcanic black sand. A space mission to an object in that region could investigate what makes it different. Often, we don't know what's weird or interesting unless we know the context it's in. The observatory will be further able to alert operators to changes in the night sky within 60 seconds of spotting them, which could help space agencies quickly plan and deploy a mission toward rapidly moving objects of interest. This could also give scientists an early warning of an interstellar object, like Oumuamua, as it passes through the solar system, for instance, allowing teams to study the intruder in situ before it slips out of reach and back into deep space. In addition, Rubin is capable of giving us the prep time we need to launch a mission to intercept an interstellar object. That's a synergy that's very unique to Rubin and unique to the time we're living in. One project that is already gearing up to take advantage of Rubin data is the JAXA European Space Agency Comet Interceptor mission that will launch in 2029. The interceptor will await sighting of a visitable, long-period solar system comet or interstellar object as it passes in front of the Sun. Then, it will be deployed for investigation. Rubin could also assist with missions concerning interesting objects located close to the passage of a spacecraft as it conducts its primary mission. One active mission that could benefit from Rubin's eye on the solar system is NASA's asteroid-hopping spacecraft, Lucy. The 12-year mission is set to perform the first in-situ study of the Trojan asteroids, 2 families of space rocks that share Jupiter's orbit around the Sun. Rubin could spot smaller, fainter asteroids that lie near Lucy's path to Jupiter, offering the NASA mission some new and unexpected fly-by opportunities. As Egel concluded, with our current telescopes, we've essentially been looking at the big boulders on the beach. But Rubin will zoom in on the finer grains of sand. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.